morning, and welcome back to the basement. This is Bob here, and if you can't already tell, I've lost all the audio that goes with this video track. It's too late to reshoot it, so I'm just going to have to overdub it. I appreciate your patience for the next 3 minutes. You know, about 12 years ago, I made the decision to look for a vintage, American, quality-built lawn tractor. I was excited when I came across a 1972 Case 442. Now, the Case machine met the criteria of what I was after and introduced me to the world of Case lawn tractors. Now, Case are like a lot of lawn tractors from the early 70s. They're solidly built, welded construction, cast iron front axle, cast iron rear transaxle, but they're distinguished from the crowd by the fact that they are all hydraulic. There's no transmission connecting the engine to the rear wheels. The only thing bolted onto the engine is an hydraulic pump, and that pump is connected to the rear wheels by means of a control valve and an hydraulic motor. So their entire operation is hydraulically driven. Now, I used that 1972 Case for 11 years without having to do hardly a thing to it. It had a solidly built Kohler cast iron 12 horsepower engine, and there just wasn't much to go wrong with it. I replaced a belt here and there, but that machine served me very well. But last year, I was excited when I came across this machine. The Case Construction Company sold their lawn tractor division to Jack Ingersoll in the early 80s, and this is a descendant of the vintage Case lawn tractor that I had before. Now, this one was built in the early 2000s, and it has a lot of upgrades on my old model. It's 4 inches longer in the frame. It has a twin-cylinder 20 horsepower engine instead of just 12. And this particular one has power steering. But it's still missing something very important. And what it's missing is right up here. There's no scoop. There's no bucket. This lawn tractor is missing its loader. That's right. I intend to build a loader onto this machine. Now, before I start welding up a frame and attaching hydraulics, there's a few things we're going to have to do to get the machine ready for the extra stress and weight of a loader. Firstly, the frame is going to have to be reinforced. The frame is just fine for its original purpose, but adding 1,000 or 1,500 pounds of weight to it here in the middle is going to stress it beyond the point that it's ready to deal with. And more importantly, this front axle is going to have to be strengthened greatly. Again, this axle is very solidly built, all cast iron construction, but it's not going to hold up to the extra weight that I put on it. So that's going to have to be upgraded substantially. Along the way, I'll need to install the 3-point hitch. I built a 3-point hitch for my former machine, and I took it off when I sold it. I just need to install it onto here and install a 3-way hydraulic selector valve. Then we'll build and install the actual steel frame of the loader and install all the hydraulics to make it work. I hope you enjoy this process. I hope you learned something along the way. I know I intend to enjoy it and learn something myself. As I alluded to earlier, the front axle on this machine is a very well-built, solid cast iron. The problem is that it's not been engineered to take these kind of loads. With a full bucket, the load on this axle is going to be approaching 2,000 pounds because the full weight of the bucket is out front and then a counterweight in the back, and so the entire weight of the machine is right here at this fulcrum point of the axle. So though it's very well made, it's not up to this job. Furthermore, these front wheels are greased bushing on shaft type. Under these kind of loads, over time, it will experience potential bending, extreme wear. It's just not made for this job. So the replacement axle will be welded steel with a standard Timken bearing trailer hub. I was able to buy both of these hubs and both shafts for about $65. For wheels, the most common approach is to use something like a narrow trailer tire. and they have a substantial load rating, but they're very skinny. In a lawn and garden setting like this, we need as much flotation as we can get. The original wheels are this high flotation design. And so I decided to go this direction, which turns out to be a golf cart tire. Each tire is rated for 950 pounds and has a nice, wide, high flotation profile. So next we need to choose what kind of steel to make this new axle member out of. Its overall dimensions from the drawing are 4 inches high and a 2-inch thickness. So a while back I had a chance on Facebook Marketplace to buy some steel very inexpensively. I got 4 of these 10-foot, 6-inch C-channel rails and this 7 or 8 foot 4-inch C-channel rail for $75, which is the deal of the century. Having said that, you might assume that the 4-inch is the better choice because it's already the correct dimension, but the problem is it's only 1.5 inches in this dimension. I have some plate enough that I could make the member out of this. In fact, I could cut the plate to the V-shaped profile and kind of cut this into pieces and weld this to that other plate. And in some ways, it would ensure that I get a more accurate end result. The problem is that this web thickness here across this plane is only like 1/8 of an inch or perhaps 3/16. And to bring it out to anywhere near 2 inches, I would need to put a piece of 3/8 or 1/2 inch plate here. I think I have 3/8 plate. And that's going to result in an uneven strength between the front face and the back face. One of the vertical faces will be this 3/16 thickness, and the other one will be twice or even more thickness. And the end result of that is going to be a tendency for it to want to twist. On the other hand, I can make it all out of here. I simply need to rip this to a give or take 4-inch width and then take 2 corresponding L-shaped pieces and put them together in a box that's 4 inches by 2 inches. And that's the route I've decided to go. So to do this, I need to rip about 48 linear inches of this product. To do the ripping, I'm going to be using this Harbor Freight metal cutting saw. Like a lot of Harbor Freight electric tools, its overall quality is not amazing. It wasn't built to last the ages. Nonetheless, it does do what it's designed to do. It will cut this steel, and it's a nice, clean, straight line. Very, clean, sharp edge, which is just what the doctor ordered for this particular operation. So I'll set up the included fence that came with the saw to 3 11/16 inches, which is what it takes if I invert these 2 L's and butt it up into here. The result is a 4-inch high member. So I'll go ahead and cut one end off to give me a clean end, and then cut it off 48 inches later, and then go ahead and rip it. Alright, so here we are with what will be our homemade square tubing. 2 pieces that invert L stack and produce 2 by 4. So for this center bevel joint that's 15.5 degrees, what I've decided to do is I'm going to pre-cut these to that precision bevel. And one of them we're slanting this way, this one we're slanting the opposite direction. But the reason I'm cutting them in advance before I join them into a solid box tube is because on the inside of the tube, where this bevel cut is, I'm going to weld in a 1/2 inch reinforcing plate that will be inside of the tube and will serve to reinforce across this kind of bowstring area here. This is 1/4 inch web material in this vertical plane, and that's beefy, but between the fact that it's, in my opinion, a little bit marginal of being heavy enough, and the fact that my welds are probably not going to be, one for the record books, by putting a reinforcing plate behind both of these faces, it will, I think, easily reinforce it to the strength that it needs to be. So, in order to put that reinforcing plate up inside that tube and weld it here at the ends of the reinforcing plate, I have to weld it in place while the tube is open, obviously enough. What I will effectively do is create a front and top half with a welded reinforcement plate, and I will create a bottom and back half with its own welded reinforcement plate. And then I'll weld these together into one solid member, and then I will drill for this tube to be welded in. So here we have the reinforcing plates cut. This one will go in this position here. I will go through and bevel the visible sides of these that I'll be welding from. We will bevel undercut here to get good join and penetration. And I would note that I beveled this angle spot right here. It was cut to a sharp angle on the bandsaw, but I went ahead and gave it just a bit of a rounding of that corner to try to eliminate the possibility of a stress riser happening right there at that spot. Probably overkill. I mean, all things told, I'm not greatly overloading this steel member based on what it's made of, but I know enough of engineering to overbuild it, not enough to build it just right. So when in doubt, I will overbuild it a little bit. And the price I pay is I use a little bit of extra of these scrap materials I have sitting around. And when I'm done, it may weigh 15 or 20 pounds more than it really needs to weigh. Those are both prices I'm happy to pay in exchange for confidence that it is safe and long-lasting. Alright, so here you can see I have the reinforcement plate in place. I've tacked here, here, and back here. It'll be welded here and lightly here. This is the most important one because there's going to be tension across this plane here. As the weight tries to break the beam, it's going to create a tension across here. So these are the key welds of stopping that stretching from happening. When you're welding stuff, one of the things you have to take into account is the movement of the metal. The weld puddle is molten metal, and it's in a very hot state. As it cools down, it contracts. So for instance, this weld puddle, while I was welding, it was molten, and as it got hot, it contracted. So it pulled this plate against this plate. Same thing here. If I would have tacked on these 3 back corners, for instance, it would have locked the piece in rotationally, but it would have tended to suck this back edge against the rail and actually kick this edge up in the air because it was being pulled so hard it would have a torque effect. So by tacking at a forward edge and a back edge, I've pulled the whole thing universally down against this face. So now that this face is even with this face, I can now clamp from here to here and be confident that these 2 pieces are in the same plane. Sitting here looking at it, I'm actually going to open that up. I'm going to open that up a 32nd of an inch. I want a little more gap there for that hot puddle to penetrate past these 2 plates and into that rear plate. I'll run a 1/8 inch 7018 rod, about 140 amps, and burn that in nice and deep. Good penetration and good size bead. I'll bring it back when that's welded. And here it is. I've had 2 passes through here, tying this plate into this vertical plane. I filled that just a little bit from the inside. You can see I have a couple occlusions there. I'm not really worried about that. That's not a plane in which it needs to be terribly strong. It's under compression. And the main weld, I didn't even bevel inside there because the real weld there is out here, where I beveled back pretty well and then filled. I think that's 3 passes there. I actually wasn't even going to weld from there up, but I realized that I need to because I'll be cutting this hole for the axle pivot with a hole saw. So I at least need some steel in the center of where the hole will be to guide the pilot bit, which will of course guide the rest of the hole saw. So I will do the inverse one, the exact same method. The only trick is with the inverse one is after I have tacked one of the sides on, after I've tacked this plate to one of the halves, I'll set up the gap and then I'll go ahead and clamp it to this piece so that the angle of the second member is a perfect join to this one. I no longer care exactly what angle this is. This is now the angle that it needs to be. So I'll align the other one to this one and then do my tack in that position and then unclamp it, finish welding it all up, and then they should mate back together very nicely. I have the inner plate tacked right here. I'll clamp them together and do a tack right down into there. Take it back apart and go weld the back. Just wanted to show real quick, you know, this thickness of this web's like a 1/2 inch thick across the 45 of this corner. And in order to get the strength out of it, it's important that the whole thing be filled with molten metal. So as you can see, I have V'd way down in there so that my rod will begin creating its initial puddle way down inside there, you know, and bridge that gap with puddle, and then come back with 3 or 4 or 5 passes, whatever it is, to fill that all back in, so that when we're done, there will be a solid, you know, channel of steel bridging all the way across that gap. Alright, well here it is before I hit it with the flap disc. Now the key here, this is the reference face that I will lay flat on the mill. So I can't have any of this bead build up here. I'm going to have to clean this off. The other side, I think I'll just go ahead and leave the bead there. It's merely cosmetic on the other side, but for this side, I need it to be nice and clean and flat. So I will clean this off. But bead looks nice. It's well filled in. I'm pretty confident that this is going to be plenty strong for what's asked of it. Nice slow speed. So there is the first level. Now I just have to keep on going, engage down below, and get the pilot hole drilled through. I don't have quite enough travel to get all the way through from this side, so I'll just get the pilot hole through, flip it over, relocate on the pilot hole, and drill from the other side. Alright, and there's our hole. Most of 2 1/4 inches. It might be a 1/16 of an inch too small. I'll measure it here in a minute. Alright, now here we are working on what will be the actual axle pivot housing. I have it laid just to skin it clean, and then I'll get it to the exact length that it needs to be to where it will fit into the tractor. And then I'll go ahead and weld it in place, and then I will bore it to receive an oil light bushing. So, you know, one of the problems with these tractors is the wear, where the 1.5 inch shaft goes through here, and the wear between this part and the shaft. So I'm going to be doing a couple things to deal with that. There's a common fix that's done where you put a bolt through with a couple big thick washers and you squeeze this whole bracket together. And I'm going to be doing that. But before I do that, I'm going to make a couple changes that are going to help it to wear longer. One is I'm putting an oil light bushing in here. So this will actually not be bored out to 1.5 inches. It'll actually be bored out to 1.5 inches plus, I think it's 30 thousandths. And then we will press fit an oil light bushing in here which will lubricate this rocking against the 1.5-inch shaft. The other thing is that the end play where every time you drive forward, it's pushing this axle back against the frame of the tractor. So I've ordered a couple 50 thousandths thick wear washers, high carbon steel, very, very slick shim washers. And those will go between this and the frame that it slides up into, so that it has this additional slickery wear surface. Of course, it will all be greased, but it will just help the thing to have a longer service life before it has to be taken apart and fixed. So to that end, I have taken the original axle out. So here's the original axle. I actually cleaned off a spot and used a mic, and I'm getting 2.275. So the part that I make needs to be 2.275 minus the double thickness of the 48 thousandth washers, one at the front, one at the back, which makes it 21.75. So this is currently 23.66. I took the part out, I very carefully measured it, chucked it back up. So 23.66, I'm going to take off just shy of 200. I'll grab a calculator and figure out exactly what to take off. And then using this DRO that measures travel of the carriage, I will take off exactly that amount. Alright, so here is our axle, pivot housing. It's the same thickness as this, minus 100 thousandths, which gives it room for these shim washers on either end. Now, next, we will go ahead and weld this in place, and then we will bore, right here in this machine. And what that should ensure is that as straight as the housing is in the machine now, then this slug will be straight with it. So I'll go ahead and clean this all up, bevel it back. We want to be sure that our weld penetration gets all the way down into this meat of this reinforcement. So this will be beveled back quite a bit. And then we will weld this in and begin boring. So here you can see where I've used an angle grinder and a carbide burr to bevel this back so that my weld between these two, will penetrate deep down into the interface between them. So here we are, it's been welded, and we're back in the mill. I left the setting on the mill the same, so when I put it in and push it down, that orientation is all the same. The only thing that is maybe not the same is left-right orientation. So put the wiggler in and bring it down, and that shows me that I'm, give or take a 1/4 inch off of my original orientation. Just to try to keep things consistent, I'll go ahead and loosen the vise up and slide it over so that this pip in the middle of this shaft, lines up underneath that wiggler pretty close. And then from there, I'll use the wiggler, left-right travel, to get it centered up. It's important that it be planar, and it's important that we be close to the center of, the beveled cut. Alright, so I have just used the bench vise to press it in. Didn't take very much force. Like I say, I have about a thousandth and a half of interference fit, and this bronze squishes pretty easily, so that was not a big deal. Now, this bushing is a little bit too long. The other side is flush, the bottom side is flush. This side was sticking up by, it's only about 1/8 of an inch, I think. So I just used this, I left this mounted up, brought it down until we kissed this surface, and then used it basically like a face mill. So this part of it is now complete, with this exception. Now it needs to be able to be greasable. It should have a grease zert on top of it. So in order to do that, I'm going to have to drill through the plate and into this housing, and then I'm going to have to thread this. I'll have to drill it, tap it for 1/8 inch pipe, screw in a little 1/8 inch pipe nipple, and then insert the grease zert into the 1/8 inch pipe nipple. Alright, so it turns out that this 5/16 bolt is about the right size for an extension tube to get down in here. So what I will do, I will cut this off to where no matter how tight I get it, I don't go too far into the channel. I don't want, to push this all the way past the bushing. So I'll cut this off a little bit, and then in the lathe we will through drill this to, I don't know, something like 1/8 of an inch, just enough for grease to squirt past it, and then tap this end of it to fit this grease zert, which turns out to be 1/4 28, and I don't even see any taper to it. So I won't tap it super deep so that this will kind of start, bearing down in the threads and lock up. Actually, I bet it's supposed to seat on that little beveled edge. Okay, I'll do that. Drill and tap it deep enough that it can come in and lock in on that beveled edge right there. So when we're done, this bolt head will be sticking up right here, and that grease zert will be just like that. Alright, so here is our extender. Through drilled that on the lathe. In here I've just took a little burr and just created a channel all the way around so that when you pump the grease in, it can make it all the way around the shaft. And then gave it a little bit of a spiral top and bottom so that it can work its way out to the edges of the shaft as well. So it's not greasing just the center, but it's greasing the whole length of it. I'm confident it's far better than factory was, and I don't think this work will have to be redone for a long, long time. So one of my favorite things that happens from time to time is a sense of serendipity. A sense of coming across just the right thing for what you need. And that has happened here. So what we have mounted up here is the 5-inch high housing for the spindle that will be welded onto the end of the axle member. I just cut it off the bar, at give or take 5 inches, chucked it up using the steady rest. There's a lot of stick out here, so the steady rest is helping it stay steady. Meanwhile, I need to bore through here. It's a 1-inch spindle that's going to have bushings at the bottom and the top. The bushings will be counterbored to receive the bushing. But I need a through hole all the way through, and I need to not do it from each end, because that, if I drilled from both ends, that would tend to have the holes somewhat out of alignment with each other. By having a single through hole, you're kind of guaranteed that they're nice and in alignment. And I need it to be just slightly over 1 inch. I don't want to make it exactly 1 inch, because then my 1-inch spindle may, kind of wear on the steel instead of on the oilite bronze bushings that I'm going to be putting in there. So you want a little bit of clearance between the steel spindle and the steel housing. So I said all that to say this. I first through drilled it with a standard 3/8 bit as deep as I could go, and then when this was done, I took over with this and pecked until I got all the way through. So then it had a 3/8 bore all the way through that should be pretty close to concentric. Then, like I say, I needed a drill bit just a smidgen over 1 inch, and hopefully long enough to go all the way through. Now, this is a standard 1-inch Silver and Deming drill bit that came with my set of bits. And my initial plan was to go through with this bit. If all else failed, I would go through with this bit, kind of having to peck anything after, 2 inches, which was going to be a long and arduous process. Maybe drilling in 1/4 inch, backing out, cleaning out the flutes, oiling it up, back in another 1/4 inch, and having to do that for 3 inches. But as it turns out, what I have sitting here in my rack of drill bits is something I found at an antique store a while back. And I carried it home because it was pretty handy looking to me. And it's 1 inch and a 32nd carbide tipped drill bit. And that's the reason I bought it, really. It was carbide tipped. 1 inch and a 32nd carbide drill bit that happens to be a long reach drill bit. And I say all that to say that if I were to get on the web and try to order a tool that was the perfect tool for drilling this bore in this 5-inch thick piece of rod, this drill bit is what I would have ordered. And as it turns out, it was sitting here in my rack. I think I paid $2 for it. I did sharpen the carbide using my little diamond grinder over there, but other than sharpening up the carbide, I didn't have to do a thing to it. Mount the thing up, drill away, and just finished drilling all the way through. Next, I will bore this to receive the bushing on this end. I will do a counter bore in here to the depth of the bushing, 1 1/8 inches, and then I'll flip it around, face the other end to 5 inches, and counter bore the other end to receive the other side of the bushing. So now we have our 2 spindle housings complete. Bushings pressed in both ends, and a 1-inch shaft can just be pushed up in there. It has a nice snug fit. So now that those are done, we move on to welding these housings onto the axle. So I have since used a digital protractor, measured the angle off of the drawing, scribed it, and cut it on the bigger bandsaw. Now, the next thing you can see I've done is I laid the part on here and scribed an arc. And I have since taken the grinder with the cutting wheel in it, and I have ground out these arcs. This is particularly important. This web here is only 1/4 of an inch. This is not, terribly thick. I mean, I will weld all along this edge, but this isn't where a lot of our strength is coming from. A lot of our strength is coming from these heavily gusseted ends. And the bottom one in particular, because these are slanted outward, the pressure is to try to break the bottom off of the axle. So on the bottom one in particular, I've taken great pains to V the joint out so that we can get weld penetration all the way down in there to weld this entire thick meat here onto that bottom end of that spindle housing. This is now nice and secure. I have gone through and removed any high spots so that it's not rocking and rolling. It's not in any way imprecise as far as where it goes. It's very clear where it should lock in. I will tack it in the middle of each side first to try to suck it into place, and then in particular on this bottom one, this first pass, I will burn very hot so that it gets real good penetration both into the spindle housing and into this thick meat of this axle member. Here it is after welding. I started deep down in that V at about 145 amps, burning really hot so that I got a good melt into this metal and into that webbing of that steel. And did a single pass over the whole thing real hot, and then in the thickest part did like a half pass. Then I came back, put it back on about 120 amps, which is where this 1/8 inch 7018 rod really likes to burn, just welds like butter. And just kind of took 2 passes to fill in, and then this is just a covering pass. The welds are already rusty because after each and every little weld segment, I had to grab my water bottle and blast the thing off to cool it down so I don't overheat these oil-eyed bushings. In a perfect world, I would have welded this up and then machined it. But getting this set up into the mill vise with any kind of accuracy was going to be a huge challenge. So I figured it made more sense to just build this part on the lathe, get it, completely assembled, and then weld it up and just keep it cool as I'm welding. Here's this side over here. And then if we put it on its side, these are the initial tacks that I made. So when I came back to cover pass, I got, some weld porosity right there where I burned over top of the tacks. This side didn't do it as bad. So this member is complete. It's time to move on to building some spindles. Okay, we're back. So a couple days has gone by, and I don't mind telling you the last couple days has required a very challenging level of thinking and analysis and research to figure out where to go from here. But I have figured it out, and so let's talk about it for a minute. So for any four-wheeled vehicle, when it makes a turn, the track of the 2 front wheels are different. The inbound wheel is turned relatively tighter than the outbound wheel. The reason this is true is because the inner tire is turning on a tighter radius than the outer tire is. the angle of each of the two front tires should intersect with the angle of the rear tires. Therefore, the angle of the front tires in a turn is a function of the length of the wheelbase and the position of the control arms. So in my design for this front end, which is basically a copy of what was already here, this control arm will be welded right here, and it's providing the support that the weight of the axle and the weight of the whole tractor will rest on. I'll actually have a needle roller bearing in this interface right here to help to make the steering easier under a heavy load. But this half-inch plate will be supporting all the pressure of the front end of the tractor. So initially, I had just assumed that I will weld it in whatever position and just connect these two across here with a tie rod. But when I got thinking about it, I knew that in a turn that these two wheels have to take on a different angle. And I didn't mentally know what controls that angle. Well, it turns out that the angle is controlled by the relative position of this control arm. In a tight turn, if the control arm is perfectly straightforward, then the tires are perfectly in line with each other. They're parallel. But in a tight turn, if, for example, the inboard wheel is in the appropriate turning radius, the outboard wheel will not match up to its radius. Now, if we rotate the control arm to the inward position and then put the machine into a tight turn, the problem gets even worse. Here, if, for example, we set the outbound wheel to be on the proper track, then the inboard wheel is way out of its proper track. So the solution, it turns out, is that the control arm, if it's in the front of the axle, has to be an open stance. It has to be angled outward. The exact degree of how far it's open, I couldn't really find a formula for, so I just played with it in CAD until I found a number that satisfies both the track of the wheels under a tight turn and the track of the wheels when you're heading straight forward. And that number turned out to be 18.5 degrees if the control arm is facing towards the front. Now, another option is to have the control arm sticking out the back. The result is the same idea, except that if the control arm is sticking out the back, then it has to, in fact, be an inward stance of the control arm, which is, if you think about it, it's just the same idea, but reflected backwards. However, they're not the exact same angle. If it's facing out the back, then the angle of degree turns out to be 15 degrees. Now, the original configuration has this steering control rod in the front side of the axle. And all things being equal, I would rather have it on the back side of the axle. The reason being that this rod is relatively delicate as far as it's not very substantial, can be easily bent, and if it is bent, then the steering geometry of the two wheels is changed. So having this thing up front where it can run into things is not ideal. But the problem is clear enough. There is not a lot of room behind this axle for this big steering through rod to go through. We're fighting the power steering cylinder, and we're fighting the pulleys that are driving the mower deck. In fact, the linkage that holds the mower deck itself and the belt are all kind of in the way, not to mention this structural angle bracket that the mower deck is suspended from. So though the rear is a better ultimate option, especially for longevity, it'll be a real challenge to put this control rod in the rear of the axle. However, I've done some careful measuring, and I think by getting a longer belt that I can lower these two pulleys down. By lowering them down, I give myself a clear space here. So I think if I do two things, rework the mower deck support to drop it down about 3/4 of an inch, and rework the pulleys to drop them down about 1/2 inch, then I think I can get a free space here that's large enough for the tie rod to pass through. If I can do that, then I can cut this area out, reinforce it with some additional steel, and then my steering tie rod can be behind the axle in a much safer long-term location. Now, I'm not sure if I can accomplish that or not. So in the end, the plan that I've made is to hedge my bets. I'm going to go ahead and weld in the front-facing control arms. So this will be bored, this will go into the hole that's bored into it. This will be welded in place onto this shaft, and then they will both be combined into a single unit with this at an 18.5 degree angle. That way, down the road, I can use a front tie rod configuration, if that's what ends up being what I have to do. But if I can have a rear-facing tie rod that penetrates through the frame area, I'm going to leave this spindle extra long to give me the height that I may need to have a rear-facing tie rod. So I will build up the spindle with this extra long shaft here and figure out as I go forward whether or not I'm going to actually be able to do the rear-facing tie rod or not. If I can use the rear-facing tie rod, then these will be here, but they will never be hooked up or used. Now that I've made my decision, the next step is to go ahead and bore this. It will be bored in at an angle, a 1-inch hole, and then this I will weld to here, and then insert the whole thing into that bore hole, turn it till my angle is exactly 18.5 degrees, and then weld it up into a single unit. Okay, so I have welded this around the base of it. Now, I ran this a little hotter than I normally would because I wanted to get good and deep penetration, even though it did give me a little bit of undercut. But this is not the final weld. This will be covered with a cover pass and some support structure between this and the horizontal spindle. For now, I'll mount it up in the chuck here, and then we will turn this back side of this to be nice and flat and at a perfect right angle with the kingpin. That way, as it turns left and right, it won't have high spots or low spots. In order to tack it up, I put the kingpin through the actual axle housing and then rested this flange right against, the edge of the axle housing, which is a nice square cut, and tacked it there to get it, pretty square to begin with, and then went and, welded it in that position. So feed this in a little bit. As fast as I want to go. So you can see that we are clean through the majority of it now, but we still have this little section here that needs to be cleaned up. So I'll just keep feeding the tool in a little bit until I have this all cleaned up. Here's the setup I had to do. I'm using these needle roller bearings to support this, and it has these hardened washers to sit on this face for these needles to roll against. I slid one of the washers on and I was hitting the inside radius nib there. So I sharpened up this high-speed steel tool bit, took off all the radius to where it's just really sharp, put it into where it's just skimming the shaft, and then fed it in so that I'm actually undercutting a little bit of a V groove down at the base there so that this washer can sit flat all the way into the face where it needs to get. So now that we have our two spindle kingpin assemblies completed, I went ahead and took a straight edge and a digital caliper and did some careful measuring of the inner profile of the wheel to figure out where the point of interference is going to be with the spindle, with the front axle, and with these front control arms. And I went ahead and updated my drawing with the new information. And the idea is to figure out how closely, in a perfect world, due to torque and leverage, in a perfect world I would have this kingpin very, very tight to this hub assembly to minimize the torque that the pressure on the tire is going to produce. I don't want it way back here. I want it as close up here as I can get it. So what I'm trying to analyze on this drawing is exactly how close can I get it before either the axle housing rubs the inner tire or before the control arm hits the inside of the rim. I originally had been working with 2¼ inches of the center of the kingpin from the back of here to the center of the kingpin. I've now moved that by about 3/8 of an inch. I think I can get it closer in and still not hit. So that's the measurement I'm going to be going with, this 1.943 from the back to the center of where I drill the 1-inch hole. And of course I worked out the angle there again from the drawing. And so this hole is going to go in 12 degrees away from 90. So when I put it in the mill, I'll just incline this piece by 12 degrees, and then when it drills straight down, that will be the appropriate angle. So I asked for this set of angle blocks for Christmas a couple years back, and this is my first time using them. So the idea is pretty straightforward, as long as I don't get it backwards, which is that this piece is going to be mounted up into the machine, and then we're going to drill through the center of it at a certain distance from this end. So it needs to be mounted at 12 degrees precisely. Now there's a couple ways I could figure that out. I could carefully scribe lines that are exactly a known distance apart, and then try to measure the height between those two lines, because Pythagorean's theorem would tell me, for any 2 points that are, x distance apart, that if you've traveled this far in this plane, then it will have risen a certain amount. The rise to the run kind of a calculation. The problem being, and I guess I could mount a dial indicator into the machine, into the spindle of the machine, and then move the table left, right, and use the DRO to know exactly how far I've traveled. That's actually not a terrible idea. But here's what we're going to start with. We're going to take a 10 degree and a 2 degree angle block. And I'm going to stack them properly so that they don't offset each other. And the result is 12 degrees. So set our angle blocks into the mill vise on what should be the center, but it's not as important that it's perfectly centered as it is important that they are parallel. And to that end, I'm going to put it hard against a stack of parallels, which should be a 1/4 inch, and that should put this angle block very near the center of this bar. And then we're going to set the bar onto the angle blocks. So now it's riding cleanly on the angle block, and it has exactly a 12 degree angle of inclination. Now you can imagine when I start trying to drill down into this spot, the drill bit's going to want to wander back and front and down this hill. So to counteract that, I just marked where I'm going to be drilling and grabbed a big square file that's a real heavy cut because it's going to be fast. And I've kind of filed a flat notch in the place where the drilling is going to happen. Now, of course, in the process, I filed off my scribe line. So I'm going to create a new scribe line. I've hit it with blue Sharpie just so that I can see where my scribe line is at as it scrapes off the Sharpie. And now I will center up on that point. And then we'll begin with a spot drill just to, get the bit started accurately in that spot, go in the right direction. We're going to 1 inch. So I always drill through with a 1/4 inch pilot bit, and the 1/4 inch just kind of makes room for the web of the big 1 inch drill bit, and just makes it drill a lot easier without fighting back, and gives the big bit kind of something to follow. Alright, now the last thing I'm going to do, just because I can see it's going to be a potential problem, is before I drill with the 1 inch bit, I'm going to grab a carbide burr and I'm going to open this up here so that I have a more or less flat cone to receive the initial shavings of the bit. It doesn't have to be perfect, but this side, it's going to hit only this side for the first, whatever that is, 50 strokes. And that is going to tend to kick it over, to the side. So in order to counteract that, I'm going to open this area up with a carbide burr before I drill. Alright, now at least the 1 inch bit will begin its engagement and its self-alignment process without Now see, there's where the DRO comes in handy. I'm going to have to move the table to get the bit in. There we go. And then bring it back to 0. I'm telling you, having a DRO changes everything. And bring our speed way down. There we have it. Voila. So, now comes one of our critical moments of truth, which is that I will grab the bearings and that, attach this hub onto this shaft, and then attach that wheel onto the hub, and slide the whole thing up into the axle for the first time to confirm that the positions are all where I think they are, that this control arm is not striking the inside of the rim, that everything is going to work. Obviously, if I needed to make a meaningful change now, it would be a real pain, but better now than before I've done the second one. Well, wee-ha, what do you know? You would almost think that I had planned it this way. Proof of concept looks great. This needs to be adjusted to exactly 18.5 degrees inclination from there, inclination from 90 from there, and then this all needs to be welded together. So let me take it apart and let's talk for a minute about its welding. Now this part needs to be welded up in this configuration. It will have as much as 1,000 pounds of load, so it needs to be pretty strong. This is an 1.25 inch rod here, maybe 1 1/8 inch. It's not very big. Having drilled through it, I have just about cut it in half, really. So, although there's plenty of meat here to act as an alignment for me to get the shaft in here straight and properly, there's nowhere near enough meat to just kind of do a little bead top and bottom and assume that it's good enough. It will snap off. So, we're going to do a couple things to help that. One is that I'm going to disassemble it, and we're going to V out, in particular, the interfaces on this side of the shaft. The real strength needs to be through, a solid piece of steel, down the kingpin, out the spindle. So I'm going to make sure and V these nice and deep so that I get a real good bond on this weld. The second thing I'm going to do, once I have cut a bead in, here and here, then I will go ahead and cut and install what is essentially a triangular reinforcement that will come out to here and will try to transfer some of that bending load up to this member. If I can reinforce between here and here, then I get effectively this entire web as the strength of the axle. And then while I'm at it, just because it doesn't hurt anything, I'll go ahead and backfill this crack with weld so that the back end is kind of tied in as well. So I found myself really struggling to have confidence that I could accurately measure this angle of this arm sticking out of this shaft, especially because I had to bend this member in order to get it to fit up inside the hollow of the wheel rim. And so the angle actually runs through the center of this ball stud, and the ball stud lost its one-to-one relationship with the flat of this flange. So I had to measure from the center of the shaft at the point that it leaves the housing down here up through this ball stud. That's the actual plane that has to be 18.5 degrees. And like I say, I fiddled with it, and ultimately I lacked confidence that I had it close enough, especially when you consider once I burn this thing in, it's going to be very difficult to go back and change. So I figured it was worth the time to go ahead and build the whole thing up here on the bench. I was able to accurately measure from the end of this spindle. The end has now been cut off, but I was able to accurately measure from the end of the spindle to the end of this tie rod. And I was able to at least identify that I got this one in the same relative angle. And then when I did that, this piece of plywood here is as a measuring device. This provides a plane of, that's perfectly longitudinal to the tractor, right? So then I can measure between this plane and this plane using a digital angle gauge. So first thing I found is that with this shaft sticking out the back, I couldn't turn the wheel the fully specified range, which for my purposes is 48 degrees from straight ahead to a full turn. I don't know if that is greater or less than industry standard. Looking at it on the CAD diagram, it looked like a pretty sharp turn, and it's definitely sharper than the machine can turn now. So I took them off, cut them off, and then you can see here where I had to groove out a little bit as well, just to make a little room for the tie rod to have space. Speaking of the tie rod, all I did for the tie rod is I turned a piece of 1/2-inch fine thread rod. This is just basically fine thread, 1/2-inch all thread, and then turned this solid threaded plug and screwed these tight together into here so that this is screwed hard up against that shaft in there, and they're kind of locked together right here. And that way, without modifying the original tie rod, I have basically lengthened it by 2 or 3 inches. So right now, at this kind of steering lock position, it's at 48 degrees. On the drawing, when this one has turned to 48 degrees, then this angle back here should be 54.1 degrees. And I will tell you, I was pleasantly surprised and maybe even shocked when I measured it, and as nearly as I can measure, the slightest tick away from precisely 54.1 degrees. So it looks like, by dumb luck if nothing else, that I got the thing right. Everything is upside down, so use your best upside down imagination skills. I'm going to try this O-ring. It's just a plain old black rubber O-ring that's about the right inner diameter. And just use the O-ring to try to, seal the gap to prevent dust and grit incursion into that precision part in there. So here it is, ready to install. It's been painted up. I made these collars to retain the kingpin in the housing. There again, I'm going to try to set the steering up to work from the top, not the bottom. So for now, I've left these kingpins way extra long because I'm not really sure, what I'm going to need. But I can always cut it off later. Got the grease zerks in. It's ready to go ahead and install these hubs on the shafts. I just finished making this pin. This pin goes through here, through the center. And it's a style that people sell on eBay, that this back cap is trepanned out a little bit so it can actually telescope a little bit over the end of that shaft. The idea is that you can actually, using this bolt, squeeze this so that these flanges that this axle rides in, you can actually squeeze the flanges against it to get a tight fit, which limits the fore and back play that it would have. So I didn't really invent it, just need the right size shaft here, you need a flange here, and then a flange in the back that has this trepanning so it can squeeze up tight. And then I made my own lock nut. I stuck it in the vise and squeezed it till it was a little bit out of round, and now it clamps on there real tight. The idea is that we're actually not using a lot of tension at all, just enough to, apply some pressure, but we don't want it to back off. And I got lucky, went in my bolt drawer, and I had a 1/2-inch bolt that was exactly the length that I need. So, hooray for me. So with the axle about complete, I'm now moving on to the next point that needs to be strengthened. We now will have a new, stronger axle, and all the load of the axle will be transmitted to this pin, and then this pin will transmit it into the frame of the tractor. So at this point, we can expect it to have
under a dynamic load up to about 3,000 pounds of pressure. So the old frame here is made of a sandwich of 1/4-inch plates that are welded into these 1/8 inch thick. They're slightly more than 1/8 inch. They're 140 thousandths, whatever that is, of these C channels. And then worse yet, that relatively light duty C channel has been notched to make room for this motor base because the engine is taller than the original generation of engines that they put in them. So they kept all the original dimensions and they just notched this frame downward. But there again, now the frame is even weaker because it has this notch out of it and we don't get the full height of the vertical member. So in order to rectify all that, to make sure we don't bend and break and tear up this thing when we put it under a heavy load, first thing we're working on is this reinforcing bracket that I have clamped against the existing 1/4-inch plate, and then I will weld them both front and back, the back corner that you can't see. And then this solid unit will slide into this pocket and will be welded here and here so that it will kind of join the frame. So then at that point, we'll have a good, this is 3/8 steel, we'll have a good solid point out to here that is, plenty strong enough for what's necessary. From there, I will bore through here with a 1-inch hole saw. I have to transmit this load across this gap, and having given it some thought, bore through and then weld a 1-inch shaft, weld here, weld in here, and that should kind of unify this outer frame member to kind of joining the inner frame. And then from there, I will sister onto here. I'll custom cut a piece, a reinforcing sister piece that goes down to about here, up to here, and it travels down that frame rail back towards this pedal. So we will have this reinforcing piece to strengthen it. Now what I will do to attach it is I will drill the new piece about every 4 inches. I'll drill through it with probably a 5/8 hole. And then I'll be able to weld and fill in the hole, and that will serve to join the new frame to the old frame. A big part of what we're doing here is we're going to be using the vertical steel piece. Steel, when it's kept vertical in this way, is incredibly strong. It loses its strength if it can twist. So we want to bond these two members together so that they have to act as a single unit and cannot flex and bend and twist apart from one another. So our strength will come from the axle through this member out here to this reinforcing plate and then off to the subframe that will hold the loader itself. So new axle is installed, sitting on its own wheels for the first time. As you can see, I went ahead and replaced the tie rod ends. I picked up a set off of Amazon for $12 or $14. Shifting gears a little bit, you can see that I have welded in this reinforcing plate, and then this steel bar is what's going to act as the end of the triangular support brace. The posts for the loader will sit in this vicinity here. They'll come straight up, and then there will be a triangular support brace that comes down, and then that support brace will tie in somewhere in this vicinity. This piece is just sitting here, it's not attached because I haven't decided on a final length, and the reason I haven't decided on a final length is that I need to look at interference of things like this axle moving up and down and the cowling that's going to go over here. So I have to make my final decision of the length of this bar. So next what I'm going to do is get the steering cylinder hooked back up. Now my design spec is that these front wheels, the inner wheel of the circle, should turn 48 degrees off of center. This cylinder has exactly a 4-inch throw. So putting that into CAD and playing with it a little bit reveals that we need an arm that's 2.96 inches from the center So first we'll get this end connected, and then we'll get that end figured out. Well, it's 2 days later, and I've made some meaningful progress. We're about to take it out and give it a test spin. I've had to make a couple changes that I didn't anticipate and that were frustrating. The first is I intended to attach the steering cylinder to a bell crank up here, and as it would rotate through, it would hit this bar that I intend to use as a support, as I talked about, a triangular support up to the loader vertical post. So I kept envisioning making this shorter and shorter so it would swing past, and I had ideas of building some kind of a support that would go up and out, but of course this cowling hits as well, so that becomes a problem. But then I had it jacked up, and as I was articulating it through all of its motions, I discovered that it hits here. The bell crank, when the axle is fully down on this side, the bell crank would strike right here. This is what's called a snap fast attachment. It's Case Ingersoll's proprietary way of attaching a front device, and I'm not willing to give up that capability. I don't want to modify the tractor beyond its original ability to connect to. So that meant that the steering cylinder had to be connected down below. So I cut an ear. This is 3/8 plate, being careful to keep the correct distance from the center out to here, and then worked out. I had to play a bunch of games. Basically turn the wheels to full right hand lock, extend the steering cylinder all the way out, and tack welded it in place at that position. We know that when the steering cylinder is fully extended, that this wheel should be on full right hand lock. So tack welded it in that position, and then put it through all of its motions, and everything worked except this tie rod then strikes right there. As this comes all the way up to this point, the tie rod's trying to go straight across here and hits it. So I devised this ugly contraption to get around that, and basically it gives us a dog leg in our tie rod, but it retains the ability to adjust the toe end by using just a single rod. The only time the dog leg matters at all is when it is on this full right hand lock. All the other times it's just sticking out in an uncomfortable direction for no reason. I could have at least done the same thing to the other side. For looks' sake, it would at least look more official, I guess. However, I'm hoping not to have to use this at all. I want to actually drive it and operate it and confirm that everything works the way I think it works before I move on to the next step. Over here, the steering cylinder is simply mounted underneath the old bracket. I did bend the bracket. I bent it downward so that it can angle downward a little more, and I curled it under. I bent it down and away from me. The reason being that on full right hand lock, the rubber is now touching the cylinder. I'm going to evaluate, what's hard to guess sitting here in the shop is how high this deck is going to come up when you raise it up. However much room I have to push the cylinder into this space, then I will do so. I would love to move it an inch. I'd love to move it 2 inches into this space to get this angle of the cylinder over here and stop this rubber from hitting it. But I can only move it as far as the raising the deck will not strike it. So we'll get it out in the yard and find out how much space I have to move. Meanwhile, last thing, the hoses were now too short. This whole thing used to be up here, now it's down here. These hoses were too short. So I got on the lathe and turned some extensions. Basically all this is the, I think it's JIC internal fitting, 37 degree flare. Anyway, turned an internal fitting on this end, turned an external fitting on this end, and it just serves to lengthen the hose. This one is about 1.25 inches, and this one is like 7/8 of an inch of extension. And that just gets my hoses where they are long enough without being tugged, but not so long that they're just flopping all over the place. All right, well, the test drive was successful. What I found is that, just as I suspected, tractor does rub right there against that cylinder, which long term that's not going to be good. So I'm going to make a couple changes. First of all, the tractor is currently turning tighter on a hard right turn than it is on a hard left turn. Because it trims, mowing wise, it trims on this side. That's not a great configuration. I'd much rather have it turn harder the other way than this way. So to deal with that, I will extend this tie rod end. No, not extend it. I will retract it. I will retract this tie rod end, so that as it comes up this way, it will make the right turn not as sharp and make the left turn harder. So that will help that situation. I think for now, I'll leave this mounting alone. It seems to be fundamentally working, because like I say, the right turn that it's currently doing is sharp enough. And so if this kind of acts as an ultimate stop, which by the way, I may install turn stops. I don't really see the point of turn stops when I have this power steering, that's plenty strong enough to hold against the turn. But I think I understand that under a really hard turn, the force on the wheel is to twist it inward, and that it will probably put undue strain on all the tie rod ends over time. So I think I probably will weld some hard turning stops on. But before I do that, I will get it worked out exactly where I want the turning to stop. But overall, it seems to, in my opinion, look okay and work okay. The steering is much tighter than it used to be. So this will go ahead and end this video. Phase 2, we will drop these pulleys 5/8 of an inch. By dropping it 5/8 of an inch, that will increase the space available here. We will weld a reinforcing arm here and drop this fulcrum. This is the front fulcrum of the deck. We'll drop this fulcrum down to here, so that the deck is still in the same position. It just rotates a little differently, and that will clear out this area where I can cut this out, essentially 2 inches high by 4 inches deep, and then we will run our tie rod through there and get rid of this ugly, cumbersome, and easily damaged front tie rod. And then in phase 2, we will also attach the reinforcing plates to the side of the frame. This will have to come off and be reattached onto what will then be the new frame. That's the plan. That's all phase 2. But for now, there is a new heavy-duty front axle on a Case Ingersoll tractor. And hey, thanks for watching.